Welcome to a course on complex analysis. In the previous lectures, we have seen about the concept of contours and arcs that are available in complex plane. In this lecture, we are going to introduce the concept of contour integrals. Let us explore. So, as said, we are going to explore about contour integrals in this lecture. Here, we are going to deal with the integrals of complex valued functions in the complex variable z itself. In the previous lectures also we have seen some concepts related to the complex integrals, but those the limits of those integrals were some real values. Okay, so even though this is a complex valued function, we were integrating with respect to some real variable t. Okay, here your t takes the values in this real part. So these kind of notations are available only in the in real number systems or any subsets of real number systems, but in complex number system we do not have any comparison of this sort. Okay, now we are going to do this integration with respect to some complex variable. How are we going to do that? So in order to start with this thing, we need the concept of contour, and that is what we have explored in the previous lectures. Okay, so these kind of integrals are defined in terms of the value of function f along a given contour c. So here we will be given some contour. So this contour is extended from the point z1 to z2 in the complex plane. Suppose like if you have a curve which is extended from this point to this point. Okay, this may be any smooth curve. Okay, this is one sort of a curve, this is another sort of a curve, you may have curve of this sort. Okay, so here I have produced three different examples for your understanding. So this is one sort of a curve. Okay, and let me do those things in different color for your better understanding. So this is another sort of a curve, this may be your c1, this may be your c2, and you may have any curve which is extended from this point to this point. Okay, you may have curves of this sort as well, this may be your c3. Okay, be it anything, but you must have some contour. Okay, so when you recall from your calculus and several variables, these sort of the things we call it as line integral. Okay, so it is a line integral and the value depends on the contour that we take as well as the function that we deal, right? So here we can give two different notations to these contour integrals. The first one is integral over c f of z dz. Okay, this means you are talking about, you are giving importance to the contour. Okay, you are giving importance to the contour means you consider the initial point. Okay, just a minute. Yeah, so you are giving importance to the initial point, end point, as well as the path in which you travel. Okay, whereas the later, the second notation, that is integral z1 to z2 f of z dz, this is used when we give importance to the endpoints. In which path we are traveling, that doesn't matter. Okay, so that is the situation where the second notation is to be used. And here we have an equation z which is represented in terms of some other parameter t, which means here your z is what, x of t plus iota times of y of t. Suppose this represents a contour extending from this point to this point. Okay, then what are we going to do? So that is the base assumption that we have, and also we assume that f of z is piecewise continuous on this interval. Okay, if it has to be piecewise continuous, then you can give this f of z of t, which is of the form u of t plus iota times of v of t. Okay, both your functions u and v has to be piecewise continuous in the given interval. Okay, both here, remember, your u and v are real valued functions. So hope you people can check the piecewise continuity in the real valued functions. If both are piecewise continuous in the specified interval, then your whole complex function is also a piecewise continuous function, right? Next, we define a line integral or contour integral in this form. Integral over the given contour f of z dz is integral a to b f of z z prime of t dt. Okay, so this a complex valued is transformed to some real valued, and with this idea we extend, right? Since c is a contour, okay, your z prime of t will also be piecewise continuous. So the the piecewise continuity is enough to ensure the integral value exists, right? Next, we are going to see some properties of the contour integral which are extended from the complex integrals that we have already seen, okay, and the derivatives as well. You just multiply a complex quantity with a function and integrate it is same as that of integrating and then multiplying this complex quantity, and the sum rule. And the third one, let me explain only the third one. So this involves some technicality. So if you have a function z equals z of minus t, then your t takes the values in this interval, right? So you just see, okay, if this is your point z1 and if this is your point z2, then you have a curve which is joining these 2 points z1 to z2. So this direction, the movement in this direction is c, the movement in this direction is denoted as minus c. Okay, so here we are about to do minus c f of z dc. This is minus b2 minus a f of z of minus t multiplied with z prime of minus t dt. Okay, so when you do this one, you would get minus outside. So this is minus b2 minus a, and f of z of minus t multiplied with, actually here what you are doing is that you are differentiating this one with respect to this. So you will have to make use of the chain rule. So this becomes z prime of minus t, and you will have minus 1, and that actually you will have minus 1 and then dt here. Okay, so this minus 1 comes outside, you have minus here and you have dt, right? So when you see this is equivalent, okay, we do the sign change and see it is integral a to b f of z prime of t dt. Which what we have done here is that we have replaced minus t with tau. So for minus t you have from minus b to minus a. Okay, so we are changing these to tau. So this is gonna happen, right? So for t, it is from minus a to minus b. If it is for minus t, it will change the other way, right? So we have to do those changes here. Okay. Once again, let me tell you here, this limit is for t. Here, if you wish to have d of minus t, this becomes minus a to minus b. Okay. That is one of the property of integrals, real integrals, right? So using those ideologies, it changes to minus. Actually, here you have this, and when you change this to minus t, it actually becomes minus of integral minus a to minus b f of z of minus t z prime of minus t and the derivative of minus t. Okay, this becomes like this. Now you just replace minus t with tau. So for minus t, you have from minus a to minus b. Therefore, for tau, you will have from a to b. And finally, replace tau with t and you get this quantity. Okay, this is simply what? Integral over minus c f of z dz is minus integral over c f of z dz. So this is what we have proved actually. So that is the third property. And Sometimes your curve, okay, let me erase, I think if you need this part, I'll leave this here. So sometimes you may have a curve, a contour, which is extended from Z1 to Z2 in this way, from Z1 to Z3 in another way, something like this. This may be your entire contour C. So this may be split into two contours, namely C1 and C2. So the integral over C may be split into integral over C1 plus integral over C2. This is possible. Okay. So that is what is given as the fourth property. Right. So now we will explore some examples. So the first example that we are going to consider is, we are given an integral over c z bar dz. So the function is given where c is the right hand half z equals 2 e to the power iota times of theta, where theta lie between this thing of the circle absolute of c equals 2. Right. So when we try to plot this one and see what is this region, okay, what is the curve? Actually, z is 2 multiplied with e to the power iota times of theta. So from this, okay, just a minute. From z equals 2 e to the power iota times of theta, r is 2. Therefore, the radius is 2 and theta is varying in the given interval. Okay. So from this we get r is 2. So we fix radius 2. Okay. And we will usually we draw a circle. We draw a circle of this sort. Okay. Here it is specified that theta is ranging from minus pi by 2 to pi by 2. This is the angle theta 0. This is pi by 2. This is pi. This is 3 pi by 2. If we wish to transverse in the positive direction, this is the case. What is minus pi by 2? If you travel in this direction, you see your 3 pi by 2 is equivalent to minus pi by 2. So what is given? Which means the part that we are going to consider is only this quantity. In this direction we are considering. Right? So we have seen what is the contour over which we are going to integrate. Right? The function f of z, that is given to be z bar. Okay. So by contour integration, how do we write? So integral over c f of z dz is integral over the given limit a to b, right? F of t z, actually f of z of t z prime of t dt. We change everything into one parameter t, where t is the real variable, right? Where t is real. So this is gonna happen. Now, what is gonna happen here? We change everything to theta. So if you see, your I is varying from this is minus pi by 2 to pi by 2. So we'll, as I said, we will change everything to theta. So first of all, if okay, here we'll have to write z. So for which let me do the calculation here. If z takes the form 2 e to the power iota times of theta, what is z bar? It is 2 e to the power iota times of theta whole bar. Okay, so this is 2. So this may be written as 2 cosine theta plus iota times of 2 sine theta whole conjugate. So this is 2 cos theta minus 2i sine theta. So this may be written as 2 times of e to the power minus iota times of theta. So from this, what is your z bar? It is 2 e to the power minus iota times of theta. Next, you will have to differentiate your z with respect to theta. So when you do that, okay, so your dz upon d theta is what? So it is 2 is a constant that is outside. So e to the power iota times of theta is e to the power iota times of theta and multiplied with iota. Okay. So this gives you your dz is 2i e to the power iota times of theta and d theta multiplied with d theta. So here we would have 2 multiplied with iota e to the power iota times of theta d theta. Since we have changed everything in terms of theta, here we know theta varies from minus pi by 2 to pi by 2. Okay. Remember, we must have some real quantity as the limit of this integration. We'll have to do the conversions accordingly. So here you may take 4 iota outside. So integral minus pi upon 2 to pi upon 2. We have taken this quantity outside just because it is a constant. E to the power minus iota theta multiplied with e to the power iota theta and d theta. Since the product of these two gives us 1, so 4 times of iota minus pi upon 2 to pi upon 2 d theta. So this is 4 times of iota theta over this limit. So this is 4 times of iota pi upon 2 plus pi upon 2. This gives you what? So 4 pi. So this may be written as 4 pi I. Okay. Hence the integral value, that is integral over the given contour z bar dz is 4 pi I. Okay. Here some remark that I would like to make. So let me do that in different color. Okay. So remark are some extra. Z bar may be written as we know that z bar is absolute of z squared, right? So z bar may be written as absolute of z squared upon z. So if we just replace that, okay, so iota is, sorry, integral value is absolute of z bar squared upon z dz is what? 4 pi I. Okay, I don't know if I write anymore here. You can see. So let me just write here. So what is absolute of z square? Here absolute of z squared is absolute of 2 e to the power iota times of theta whole square. This turns to be 4. So 4 is a constant. We take it outside. Integral over c 1 upon z dz is 4 pi I, which gives you integral over c 1 upon c dz is simply pi I. Okay. So from this example, we have deduced another example. Next, we move to the next problem. Okay. So that tells us example 2. Okay. Let C1 denote the polygonal path, polygonal line OAB shown in the figure. So here the contour that we are about to consider is given. Okay, this is O, this is A, and this is B, and this point is 1 plus iota, and this point is simply iota, and we know this is the origin. So this goes this way, this direction, this goes in this direction, and here it goes in this direction. Okay, and let us see what else is given in the problem. Evaluate the integral evaluate the integral I1 equals integral over C1 f of z dz. Okay, we'll have to do this where your f of z is y minus x minus iota times of 3x squared. Okay, here we know that z is x plus iota times of y. Okay, this is not the complete problem. Here I have specified only half of this problem. So this problem, okay, C1 is the polygonal line O, actually OAB, which means this is the part C1. Only this part is our C1. Okay, we are not talking about OB. By the properties of contour integral, integral over C1 f of z dz may be written as integral OA f of z dz plus integral AB f of z dz. We may write like this. Okay. What happens in OA? Let us see. So in OA, the x value is fixed, right? So x is 0. Y ranges from where to where? Y ranges from 0 to 1. Therefore, my z of my z becomes what? X plus iota times of y. Here x is 0, therefore iota y. Therefore my z prime becomes simply iota times of dy. Okay, my dz may be written as iota times of dy. And my f of z becomes what? X is 0. So y is simply y. So y minus 0 minus iota times of 0. Thus, integral over OA f of z dz, this becomes integral over y ranges from 0 to 1. We change everything in terms of y here. Okay, f of z is simply y, and this is what? Iota times of dy. We take iota outside and do the integration of y with respect to y. This is y squared upon 2 over the given interval 0 to 1. Therefore, it is half times of iota. Right, or it may be written as iota upon 2. Okay, we have evaluated with respect the first part we have evaluated. Now let us do the second thing. So in AB, the value of y is fixed. Okay, the value of y is 1. X ranges from 0 to 1. Okay, so this is the point 0 comma 1, and this is the point 1 comma 1. When we look at as the points in xy plane, this is the case, right? So from which we observe that y is fixed and x is ranging from 0 to 1. Therefore, my z is what? X plus iota, right? And my dz is simply dx. Therefore, my f of z would be what? 1 minus x minus iota 3x squared. So this is there as it is. Okay. Now integral AB f of z dz is integral again 0 to 1. We here change everything in terms of x. Integral 0 to 1. And what is f of z? It is 1 minus x minus 3 iota x squared, and dz is simply dx. Okay, if we have to do this integration, we'll have to split real and imaginary terms and perform, or we can simply perform the integration with respect to x. So this becomes x minus x squared upon 2 minus 3 I x cube upon 3 over this. So when we substitute this limits, we get 1 minus 1 upon 2 minus, actually here 3 gets cancelled, minus iota, and when we substitute 0, everything is 0. So here it is half minus iota, right? We now evaluated the values integral over OA and integral over AB. Therefore, yeah, therefore integral over C1 f of z dz is the initially we got iota upon 2 and next we got 1 upon 2 minus iota. So this becomes 1 upon 2 minus iota upon 2. So this is the value of the function over C1. Next, I initially told you, right? So this is not the complete problem. So if C2 denotes the segment OB of the line y equals x in the above figure, find I2 over integral C2 f of z dz. Okay, the exactly the same function, and with all those stuff we'll have to do here as well. Here in OB, what we have? We have x equals y with x ranges from 0 to 1. That we can very well observe from the diagram itself. Right? From here to here it is going. This is the line y equals x. It is varying from 0 to 1. So that is what we have written. And here your z becomes x plus iota times of x. Therefore your dz is 1 plus iota multiplied with dx. Okay, this may also be written as 1 plus iota times of x. Therefore your function of z becomes x minus iota 3x squared. So this is simply minus iota 3x squared. Therefore integral over c2 f of z dz is integral 0 to 1. Here we have changed everything in terms of x, minus iota 3x squared, and dz is 1 plus iota dx, right? Here we take every constant outside, so this is minus 3 iota 1 plus iota integral 0 to 1 x squared dx. So this becomes minus 3 iota 1 plus iota and x. When we integrate x squared, we get this quantity. So 3 gets cancelled, minus iota 1 plus iota, and when we substitute the limit, we would get 1. Okay, so when we multiply this iota inside, we get minus iota, so minus iota squared. So this becomes minus 1 plus 1. Sorry, minus iota plus 1. This is 1 minus iota. Okay. Suppose the C1 minus C2 is the contour C. Then integral over C f of z dz would be what? Okay. Actually, yeah. Since C2 stands first in the opposite direction, we write minus C2. Okay. So this is integral over C1 f of z dz minus, actually here we would have plus. Since it is transversed in the opposite direction, we write usually we have a minus here. So f of z dz. Therefore, these integrals here we have written this integral as I2. So for the convenience purpose, let us write this in. Okay, we have actually written this as I1. So this would give you, initially we got 1 minus iota upon 2, and here we got 1 minus iota. So this becomes 1 upon 2 minus iota upon 2, and actually here we'll have minus, right? Yeah, so minus 1 plus iota, so this becomes minus half plus iota upon 2. So minus 1 plus iota upon 2, this is the value, right? Suppose we wish to integrate over, suppose we take OAB as the total contour C, then we have C equals C1 minus C2. Okay, so this is what we get, right? Next, we are going to do one more problem. That is the third example. Let C denote an arbitrary smooth arc Z equals Z of t, where t ranges in the interval a to b. From a fixed point z1 to a fixed point z2. Therefore, integral over c f of z dz may be written as integral a to b f of z z prime of t dt. This we know, right? So now let us do one more thing. Find integral over c z dz. Okay, where c is a contour from z1 to z2. You don't know what the path is. You don't know how to parameterize these things. Okay, but from our theoretical ideologies, we know only one thing. That is, here z1 is z of a and z2 is z of b. That we know. Okay, therefore, integral over c z dz may be written as integral a to b. Z is a function of t, and what is dz? It is z prime of t dt. Okay, we have to do this. How to do it? So let us mark this as equation 1, and we observe one thing. uh, d upon dt of z of t whole squared upon 2. What do we get? So it is 1 upon 2, 2 times of z of t and z prime of t. So 2 gets cancelled, we get z of t multiplied with z prime of t. So when you integrate this quantity, you must get z of t whole squared upon 2. So back to equation 1. From equation 1, integral over c z dz is z of t whole squared upon 2 over the interval a to b. So 1 upon 2 is a constant, we take it outside. So z of b squared minus z of a squared. So this is 1 upon 2. Z of b is what? Z2 squared minus z1 squared. So this is the integral value, right? So that is integral over c z dz is z2 squared minus z1 squared upon 2. So this is same as Okay, actually before writing this is same as that of writing integral from z1 to z2 z dz is z2 squared minus z1 squared upon 2. You don't know actually what the contour is, but still we know only the endpoints. So from those endpoints we have done these things. This may be your z1, this may be your z2. So from z1 to z2 you may have a complicated path of the cert, or you might have some smooth curve of the cert. Okay, or you might also have something of this sort as also. Okay, you don't know what was the contour that you had, but still you knew that the contour is traveling from z1 to z2. So only with those ideology we have solved this problem. So with this I end this lecture. In the upcoming lecture also we are going to do few more problems on this contour integration. But before that we were in a need to see some fundamentals regarding the elementary functions, that is the complex logarithmic functions, complex exponential functions, and what do we mean by branch and branch cuts. So those ideologies we will see, and we will do problems which involves branch cuts. Thank you.